Ever wondered how we steer things in the total, absolute emptiness of space? Today, we're going to dive into one of the cleverest pieces of engineering in orbit, a technology that lets satellites navigate using nothing but invisible forces.
So first, let's set the scene. The biggest challenge with moving around in space is, well, space itself. It's a vacuum.
I mean, really think about that for a second. A car turns because its wheels push against the road. A boat turns because its rudder pushes against the water. But up in orbit, there is literally nothing to push against. So how on earth do you change direction? Now, the obvious answer, right, is thrusters, those little rockets that puff out gas. And they work great, they're powerful. But they have one huge drawback. They always run out of fuel. But what if there was another way? A method that was much gentler, but could, in theory, work forever. And that brings us to the hero of our story today, an incredibly elegant and reliable piece of tech called the Magnetorquer. You can think of it as a kind of invisible engine. So what exactly is a magnetoquarker? At its heart, it's just a system of electromagnetic coils. When the satellite runs electricity through them, it creates its own little magnetic field. This new field then interacts with the planet's natural magnetic field, Earth's. And that interaction creates a gentle push or a pull. That push generates torque, and that's what turns the spacecraft. The easiest way to picture this is to just think of a simple compass. The needle always wants to line up with Earth's magnetic field, right? Now, just imagine that needle is a really powerful electromagnet that's bolted onto your satellite, and you can switch it on and off and even control its direction. That's the basic idea right there. So the whole process is beautifully simple. First, the satellite's computer zaps some electricity through a wire coil. Second, that current creates a temporary controllable electromagnet. And third, Earth's own massive magnetic field interacts with this little one, pushing against it. And since the coil is physically attached to the satellite, that push results in a very slow, very gentle turn. It's elegant physics. Okay, so while the core principle is the same, engineers have, of course, come up with a few different ways to build these things. And each design has its own unique strengths and weaknesses. And this table breaks them down perfectly. First up, you've got the air core. Think of this as the classic, the basic concept. It's literally just wire wrapped around a frame. Then there's the embedded coil, which is a really clever, space-saving design where the coil is actually etched right into a circuit board. And finally, you have the torque rod. This one's the powerhouse. It's wire wrapped around a metal core, which creates a much, much stronger magnetic field. That makes it the most powerful, but also the heaviest. And if you want to see a torque rod in action, you don't have to look any further than the Hubble Space Telescope. What's so amazing here is you're seeing one of the 4 8-foot-long iron torque rods that Hubble uses. For the kind of mind-boggling precision that Hubble needs to point at distant galaxies, it relies on these powerful magnetic actuators. So Magnetorquers sound pretty awesome, right? And they are, but like any piece of engineering, it's all about the trade-offs. They come with a very clear set of pros and cons. Okay, on the good side, the advantages are just fantastic. First and foremost, no fuel needed. 0. As long as the satellite has power from its solar panels, these things can work forever. They also have no moving parts, which makes them incredibly reliable. I mean, there's nothing to wear out or break. And on top of all that, they're lightweight and super energy efficient. Of course, it's not the perfect solution for everything. You knew there had to be a catch. And here are the big ones. First, the torque they provide is really, really weak. It's more of a gentle nudge than a sharp turn. They're also completely dependent on having a planetary magnetic field to push against, which makes them totally useless for deep space missions. And finally, their control is limited. See, a spacecraft needs to control its rotation in all 3 directions, what engineers call pitch, yaw, and roll. But because magnetorquers can only push against the local magnetic field lines, they can't always turn in every direction they might want to. That's why they're usually paired with other systems to get the job done. But this whole reliance on magnetism can sometimes lead to some unexpected results, which brings us to our final story, a sort of cosmic fender bender. So we've seen how magnetorquers are this elegant way to steer a satellite. But what happens when that magnetic force gets a little too friendly? In 2011, something absolutely wild happened. As this quote from the mission reports puts it, 2 tiny satellites became magnetically conjoined, and it was the very first time in history that 2 satellites had ever latched onto each other in orbit without actually crashing. So here's how it all went down. On October 28, 2011, 2 little CubeSats, M-Cubed and Explorer-1 Crime were released at the same time. But pretty soon after they were deployed, the mission team realized they were stuck together. Turns out, the powerful magnets on one satellite had literally grabbed onto the other one, and they just ended up orbiting the Earth stuck together as a pair. And that story just perfectly illustrates the dual nature of this technology, doesn't it? On one hand, it's this incredibly clever, sustainable solution for controlling spacecraft. But on the other, it shows how the very forces we're trying to harness in space can have really surprising and unintended consequences. So what do you think? An elegant solution or a potential cosmic traffic hazard?